All right, so this is a long one, so just kind of mentally prepare yourself. We're going to start connecting some graphs and go back and forth with F prime and F double prime. We're really going to get into F double prime in this particular lesson. All right, so we've talked about how you can have a zero slope with no extrema. You can have max and mins where there's zero slopes or where the derivative does not exist. Um, you can have local and absolute mins on the endpoints. So there's all sorts of different things. We're just going to extend our thinking about this a little bit more, give it a little bit more formality. So we have a first derivative test. This kind of summarizes everything that we've been talking about. All right, so first of all, we can have, if we have a critical point C, so if the F prime changes, and I just wrote this out and did a little sketch on the side, you have a lot of room. If it changes from positive to negative, increasing, decreasing, you can have a local max if it goes from positive to negative, either at a zero slope or where it does not exist. F prime equals 0, F prime does not exist. So if F prime changes from positive, where F is increasing, to negative, F decreasing, that's a max. Second of all, if the sign changes from negative to positive, decreasing to increasing, you can have a local min where F prime equals 0 or where F prime does not exist. So when we're talking about interior points, your max and mins occur either where F prime equals 0 or does not exist. If you want to pause the video where you can write this all down, that's fine. Number 3 is important because this is where there is no sign change. You might have a zero slope or the derivative does not exist where it's positive to positive or negative to negative. So that's why you always need to use sign charts to verify and justify your thinking. These last two are just specifically at endpoints. There's a local max at an endpoint if there's a zero slope and on the right it falls to negative. This is only for left endpoints. It's a local min if to the right of the endpoint it's positive or increasing. This is specifically at a right endpoint. It's a min if before the right endpoint it's negative, and it's a max if it's positive on the left side. All right, so this is just really all that we've been doing. Nothing here, nothing new here. Take the derivative. Set it equal to 0. Factor, 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 factor. Or you can either factor this one, you could just solve it too. Why don't we just do that? Because we can get x squared by itself. So add 12. You have choices on this one. Sometimes if it's just plain x squared, just get it by itself. Divide by 3, square root, and make sure you always include the plus or minus when you square root. There is no interval, so we don't need to pay attention to that part. We're going to consider from negative infinity to positive infinity, looking at negative 2 to 2. All right, so let's make our intervals because I think it's just easier that way. Negative infinity to negative 2, including negative 2. Negative 2 to positive 2, and 2 to positive infinity. Then we're going to consider F prime and plug it back into the derivative. Best choice here is negative 3 plug -3 back in. That'll be 27 minus 12, positive, which means F is increasing. Then we have 0 is the best choice between -2 and 2. Plug 0 in, it's negative. F is decreasing. And +3, plug it in, positive, increasing. All right, so if we put a little graph here, and we know x to the third, this makes sense. It's increasing, 0 slope, decreasing, 0 slope, increasing. The only thing this wants are your extreme values. So we see we have a local because our graph extends on forever, up and down, so there are no absolutes. So we have a local min, and if we plug -2, back up here, let me just write this out. If I plug -2 into the equation, I am going to get 11. And if I plug +2 in, I'm going to get -21. So this is my local, oh, sorry, this is a local max. Let's go in order. Sorry. There's a local max of 11 at x equals -2. Down here is a local min of -21 at x equals 2. So these come from just plugging my critical values back into the equation to find the corresponding y value, which are the critical values. All right, let's check out letter B. It's a little tougher just because the derivative is tougher. I'm going to erase this just to make some room. Okay, so we start with the derivative. And I recognize this is being multiplied, so this is a product rule. So we take the first times the derivative of the second, which is just e to the x, plus the second times the derivative of the first. All right, when we set this equal to 0, anytime you have a product rule where e to the x is involved, you're going to factor out e to the x as a GCF. So I look at each of these terms. They both contain e to the x. So I factor e to the x out. And I'm left with that quadratic. Now, this quadratic is much easier to solve when it's in order. Now, e to the x can never equal 0, so my derivative will only equal 0 when the quadratic is 0, which is factorable, plus 3 minus 1. So our zeros only occur when x equals -3 and x equals 1. So think of your sign chart, -3 and 1. I'm going to make my intervals. Okay, so -infinity to -3, -3 to 1, and 1 to infinity. Now we're going to test the derivative, g prime. So let's try -4. Also consider the point that e to the x will always be positive. So I'm only considering my two factors of what they will be. So if I plug -4 in for x, I get a positive times a negative times a negative, which is positive, which means g is increasing. Plug 0 in this interval. and that's going to be negative. That means G is decreasing. And plug in 2, positive, positive, positive. So it's increasing. These are all zero slopes. So let's just think increasing, zero slope, decreasing, zero slope. Now it's not exactly going to look like that, but it gives us an idea. Okay. So we need to plug in -3 and 1. If I plug -3 in up here, -3 squared is 9 minus 3 is 6e to the -3. When I plug in 1, I get -2e. All right, so -3, that's a local max. So my local max is 6e to the -3 when x is -3. This is my local min of -2e when x is 1. Okay, so this was somewhat of a review. Hopefully it kind of tied some things together for you. Now we're going to get into the shape of the graph. So we know where the max and mins are. This is getting into the curvature, or what we say concavity. Concave up, concave down. So a graph is concave up if on an interval y prime is increasing. If the derivative is going up, it's concave down if the derivative decreases. Okay, so as we kind of trace this up, the steepness is getting less. So this can be a little bit confusing. This is making it a lot easier. So if y prime is increasing and decreasing, that's saying where y double prime is positive or negative. It's concave up if the second derivative is positive. It's concave down if the second derivative is negative. So where the first derivative tests increasing or decreasing, and we find maximums and minimums, y double prime finds concavity. So the second derivative is concavity, the first derivative increasing, decreasing. So let's just do something basic like x squared. So y prime is 2x. Y double prime is 2. Well, this second derivative is always positive. So therefore, y is always concave up. And a lot of times I just abbreviate C up, concave up. So think about the graph. Y equals x squared, it's always cupped up. So think about like if you pour water in, if you can pour water in and the water stays in, the cup is up. If your cup is upside down, if you pour water, it falls out. That's concave down. So at first, sometimes kids struggle visualizing. This is concave down, upside down, concave up, the cup is up. Almost sounds like a Dr. Seuss book, huh? Okay, so this one was pretty straightforward. Now let's consider this one. Y prime, the derivative of a constant just goes away. Derivative of sine is cosine of x. The second derivative, the derivative of cosine, is negative sine of x. All right, so if we consider the graph, negative sine of x is just sine of x flipped upside down. So where is the second derivative equal to 0? Well, where is sine 0 at pi? And we're looking on the interval 0 to 2 pi. So 0 is, oops, pi is where there's 0, where the second derivative equals 0. So let's consider our intervals between 0 to 2 pi. So we're going to look first at 0 to pi, then pi to 2 pi. Your second derivative never includes your values. Always use parentheses. Okay, so y double prime between 0 and pi, these are negative values. So that means y is concave down. On the right, these are positive values. So it's concave up. Okay, so our max and mins are where the first derivative equals 0 or does not exist. With the second derivative, where the second derivative equals 0, that identifies possible points of inflection. Now, what's really important is for you to have a point of inflection, there must be two pieces that take place. Okay. Number one, the second derivative has to equal 0, and there must be a sign change. Two very important pieces. So that's why you're going to be doing sign charts for the first derivative to determine max and mins. Then you're going to do a sign chart for the second derivative to find points of inflection and concavity. All right, so example 3. First of all, it's not an easy derivative, let alone second derivative. So we're going to start, we're just looking for points of inflection. So we start with the first derivative. So e is e, chain on the derivative of the exponent. So then once we do the second derivative, we have product rule because e is being multiplied times negative 2x. So we have the first times the derivative of the second plus the second times the derivative of the first, which is your e chaining on the negative 2x. So that's kind of a hot mess, right? But once again, let's simplify this down just a little bit. Negative 2e to the negative x squared. Then negative 2x times negative 2x is plus 4x squared e to the negative x squared. Now, if you'll remember, probably what I would do, we're going to set it equal to 0. We can see that there's a GCF of 2e to the negative x squared. If you factor out the 2e to the negative x squared, we're left with negative 1 plus 2x squared. So e can never equal 0. So the second derivative will only equal 0 when this portion that was factored out equals 0. So add 1, divide by 2, square root. It does not give us any intervals, so please make sure when you square root, you include the plus or minus. All right, so nice and ugly. So we're just going to use our intervals. We always start with negative infinity, then choose the smallest value to negative square root of 1/2. Never include on the second derivative. Then negative square root of 1/2 to positive square root. There's a negative there. And then positive square root of 1/2 to infinity. So now we're going to check concavity. So we're checking y double prime. And really, this is going to be the easiest place to do that because we know that this portion is always positive. 2 times e to a power will always be a positive value no matter what you plug in. So we're truly just looking at this portion. All right, so if we plug in, I don't know, -1, plug -1 in for x, that's going to be -1 plus 2. That's positive, which tells us that y is concave up. We need this because I have to show there's a sign change, that the second derivative equals 0, and that it changes sign. Both has to be true. 0 is always what I pick between a negative and positive number. If I plug 0 in, that's negative. So it's concave down. And then +1 is going to be positive. And so that's concave up. Okay, so now we need to figure out what the coordinate points are. So if we plug in negative square root of 1/2, I just get e to the negative. Now if I plug a negative in front, that's just going to be negative, and I square it 1/2. And if I plug in positive 1/2, okay, so these are my inflection points because it's where the second derivative equals 0 and there's a change in sign with the second derivative. Okay, example 4 is about graphs. So this, we have to be very, very careful about all of this. People get kind of confused about converting with the graphs back and forth. First of all, you have to pay attention to what is the graph showing us. This is the graph of F prime. So one of the things that I think is kind of important here is we need to identify certain pieces. First of all, where F prime equals 0 on this particular graph, remember F prime represents the y values because this is the graph of y prime, F prime. So this tells me where F has 0 slopes. 3 places. X equals -2, X equals 1, and X equals 4. All right. Second of all, this is where F prime is positive, F prime is positive, and below the x-axis, this is where F prime is negative. All right, so let's maybe break this up and look at all the different intervals that we have. So first of all, let me change my color. We're going to look at from negative infinity to negative 2. And then we got negative 2. Oops, that's a 0. Oh, you know what? Let's also consider where we have 0 slopes. I'll put that in. And then 0 to 1, 1 to 3, and 3 to 4. So let's talk about both the first derivative and the second derivative and how it affects f. Okay, so let's first talk about the sine of f prime, and we'll also talk about what the slope or the graph looks like for f double prime. We'll use the graph to tell us about the slope. All right, so if I look at this first interval up to negative 2, f prime is positive and it's decreasing. If f prime is decreasing, that means f double prime is concave down. All right, so if f prime is positive, the function is increasing. Because f double prime is decreasing, it's concave down. So this gets a little confusing, so just kind of bear with me. Maybe let's focus first on the sine of f prime. So from negative 2 to 0, it's still positive, so it's still increasing. 0 to 1, see how f prime is still above the x-axis, still increasing. But from 1 to 3 and 3 to 4, f prime is negative. That means my function is decreasing. So it's increasing the entire time until I get to 1, then it's decreasing. And I have 0 slopes at negative 2, 1, and 4. Now let's look at the concavity. If f prime is decreasing, that means the function is concave down. So let's maybe talk about f prime is decreasing, which means f double prime is negative and f is concave down. That's maybe a better way to think of that. All right, so what's happening here, this is where my slope is going up. So f prime is increasing, so f is concave up. Then from 0 to 1, f prime is decreasing, so it's concave down, still decreasing, still concave down, and then when I get to 3, it starts to increase, concave up. So I think part of what's difficult here, this is the graph of f prime, so we use the y values to find the sine of f prime. That tells me is f increasing or decreasing. But then we use the slopes of f prime to find f double prime. So when the slope of f prime is decreasing, f double prime is negative, concave down. All right, I've just thrown a whole bunch of stuff at you. Let's see what this graph might look like. Now, I really don't know anything about the y values. All right, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so it's increasing, and at negative 2, it's increasing and concave down, but once I hit negative 2, I'm going to have a zero slope, but it's still going to be increasing, but it'll change to concave up. So let's see what that looks like. So I'm going up and -2, zero slope, increasing. Then when I get to 1, I'm going to keep increasing, get to zero slope at 1, and then I'm going to start to decrease. And then once I get to 4, I'm going to flatten out to a zero slope again. All right, so that could be anywhere along the y-axis. What I'm going to look for, did you create zero slopes at -2, 1, and 4? -2 is a zero slope, 1, zero slope, 4, zero slope. Did you have your function to be increasing until increasing until I get to after 1, that's where it starts to decrease. So you might not have a perfect graph, but you can kind of get a general shape. All right, that's something I know everybody's going to have to work on. Let's go to number 10. Okay, particle motion we've done a lot with. This is really just SVA, but notice it's also, we could also say XVA, because a lot of times, and the book sometimes uses S, the book sometimes uses X, but the AP test almost always uses X. So just be used to that. All right, find the velocity and acceleration. That's the easy part. V of t is just the derivative of x. I'm going to put a over here just because I'm going to do some sine stuff with this one. Take the derivative of the derivative. Okay, set your velocity equal to 0. I can factor out 2. And this is factorable because 70% of the AP test is non-calculator. They're mostly going to give you stuff that you can factor. So if you are not a good factorer, that's going to be a problem. So this gives us -11, -3. That's where your -14 comes from. All right, so our values, what makes 3t minus 11 equal 0? 11 thirds. What makes t minus 1 equal 0? Oops. When t is 1, it equals 0. All right. So then we're going to look at our sign chart. What's really important when you're talking about time, when we're talking about time is always greater than or equal to 0. And we have 1 and 11 thirds. Okay, so if we test out our intervals, let's try 1/2. That's going to be 3/2 minus 11 is negative. 1/2 minus 1 is a negative. Negative times negative, that's a positive. When you're talking about particle motion, I would talk in terms of right and left instead of increasing and decreasing. If your velocity is positive, the particle's moving to the right. Then let's check out 2. So that's 2 would be 6 minus 11 is negative. 2 minus 1 is positive. Negative times a positive is negative. So that's when the particle starts to move to the left. This is slightly less than 4. So let's check 4. 12 minus 11 is positive, positive. So then it starts to move to the right. All right. So where's your acceleration equal to 0? Just solve for t. 7/3. So 2 1/3, if we plug in 1, that's negative. Plug in 3 is positive. So notice if the acceleration is negative, it's decelerating. And if the acceleration is positive, it's accelerating. All right, so what we're going to say, the particle to describe the motion, and if we plug 0 in for negative, for t, 0 in for t up there, we get -5. So its position at 0 is -5. So the particle starts at position -5 and moves left, nope, right, can't tell my left from my right, from time 0 to 1. It then moves left from time 1 to 11/3. It then moves to the right for the duration. Okay, that was kind of a yucky one, but overall, kind of, sort of. I mean, we've done particle motion in the past. It's just being a little more specific with describing the motion, and you're just using your sign chart to describe what's going on. Okay, we're getting close. The second derivative test is handy for specific values. So go ahead and pause the video to write down the second derivative test. And let's think about what this is saying. If the derivative is 0, which means there's a 0 slope, and the second derivative is negative, less than 0, that means concave down. 0 slope and concave down, doesn't it make sense? There is a max at that point. There's times I don't think about using this, but there are times this is very easy to use. You have to just recognize that you want to use it. The second part said 0 slope and greater than 0, which is concave up, that would be a minimum. Okay, so let's see how we can do that. First, we take the derivative. We did this one earlier, I believe. Set it equal to 0. Solve for x squared. And square root to solve for x. We get plus or minus 2 are the two places where the derivative equals 0. There's no interval, so nothing to pay attention to there. Take the second derivative, which is just 6x, and we just test out each of these values. What is the value of f prime of -2? -12. So if the second derivative is negative, that means it's concave down. That means it's a local max. Then we find the value of the second derivative of positive 2. Plug 2 in and get positive 12. If it's a positive second derivative, that's concave up. That means this will be a local min. Now, be careful. The local max happens at x equals negative 2. We'd have to plug it back into the function itself. This is not my y value. This is my second derivative value. The local min happens at x equals 2. If you wanted to find the actual value, you'd have to plug it back here. Whew, 2 more problems. Okay, so we're given the first derivative. Identify where this extrema of f occurred. Well, let's think about this. We find extrema where f prime equals 0 or does not exist. Well, this is just a polynomial, so I'm just going to set the derivative equal to 0. Then I have to factor. So I'm going to factor out 4x squared. Then I get x equals 0 and x equals 3. So I'm going to test out my intervals from negative infinity to 0, 0 to 3, and 3 to infinity. All right, so f prime, let's try negative 1. This is always going to be positive, so this is the only thing that's going to affect it. If I plug negative 1 in, that's negative, so it's decreasing. Plug in a positive 1, it's still negative, still decreasing. Plug in 4, that's positive, increasing. Okay. So the extrema, decreasing, 0 slope, decreasing, 0 slope, increasing. All right, so that's our general shape. So that means there's no maximum because it's always going up. This was a false positive or false negative, whatever you want to call it. This, though, we've got a min at x equals 3. So the intervals where it's increasing and decreasing, it's increasing from 3 to infinity. Decreasing from negative infinity to 3. Okay, now we're going to do our second derivative. Set it equal to 0. I'm going to factor out 12x. I get x equals 0, x equals 2. Let's do our negative infinity to 0, 0 to 2, 2 to infinity. We never include anything with our second derivative. All right, so negative 1, that's negative, negative, positive. Plug in a positive 1, positive, negative, negative. 3, positive, positive, positive. So f is concave up, concave down, concave up. All right, so where is it concave up? It's concave up from negative infinity to 0, union with 2 to infinity. Concave down from 0 to 2. And our possible sketch is just this right here. So notice it says concave up, concave down, concave up. So that kind of matches. Hey, last problem. Woohoo! Okay, so the graph of F prime is discontinuous. This is F prime. F is continuous, so be very careful. We're going to look at -4 to 4. Find the x-coordinates of all local extrema. This is F prime, so we always want to find where does F prime equal 0 and where F prime does not exist. So it equals 0, -3, -1, +1, and it does not exist at 0. Now, this says F is continuous, but F does not exist. The derivative does not exist at 0. That means a corner, cusp, or vertical tangent. So we're going to kind of investigate some of that. All right, so let's kind of consider some intervals here, because it goes F prime is positive, negative, positive, negative, positive, negative. All right, so let's kind of put that on a chart here. -4 to -3, F prime is positive, so it's increasing. Then there's a 0 slope, so I'm going to include -3. The -3 to -1 is negative, so it's decreasing. -1 to 0, not including 0, because that's where the derivative does not exist. Then 0 to 1, oh wait, this was -1 to 0 is positive, so it's increasing. From 0 to 1 is negative, so it's decreasing. And then 1 to 2 is increasing, and 2 to 4, negative, decreasing. Whew. So sometimes this sign chart really helps you organize your thinking. Be very careful. Always make sure these match. Okay, you always, where this one ends, this one begins. All right, so it goes, so I'm going to actually do the graph first and then find my max and mins from that. All right. They ask us to draw the graph from -4 to +4. And F is continuous, so I'm not going to pick up my pencil. All right. So we're going to increase to -3, 0 slope. Then decrease to -1, 0 slope. Then increase. At 0, there's a cusp or a corner, something. Oh, and we probably should be looking at concavity. So negative slope means concave down. Positive slope, concave up. See how concave down, concave up. Then we've got to the right of 0 is a positive slope, so it's concave up. Oh, whoa. Want a little concave up, but 0 slope at 1. And at 1, oh wait, we're, sorry, 0 to 1 is decreasing and concave, keep going here, decreasing and concave down. All right, and then we have a 0 slope, increasing, That was kind of yucky. Okay. All right. So we've got a local max, local min, local max, local min. Local max at x equals -3. And x equals 0. And local min, x equals -1, x equals +1. I think I got too many humps here, but all right, that's kind of our general gist. And I think we're done.